Hello everyone. I'm happy to share with you about our project. We use machine learning to predict patient survival in the first 24 hours of intensive care. We have 4 people in the team: Yuxiu, Wang, Hanjiang, Jiazheng, and I. Okay, let's imagine there's a patient and he is really sick, and there's a doctor and she is totally overwhelmed because patients generate so much data. There's basically a zillion nodes and constant signals who can keep up with 100 Hz. Based on those data, the doctor have to use her background knowledge to judge the chance of survival of the patient. It sounds crazy, right? But that's what a doctor needs to deal with in the reality. So here's what this doctor really wants. She'd like a real-time indicator of how sick each patient is. That's what my team and I are trying to do. We will use different classification models to deal with the big data in order to predict the survival of a patient in the first 24 hours and select the most important features. The first part is about our dataset. It has over 90,000 entries and 186 columns. Among those features, we have categorical features like identifier and demographic data. We have another important predictor called APEC, designed to measure the severity of disease for adult patients admitted to intensive care units. For numerical features, APEC also plays an important role, and data about vitals, labs, and you can see GOSIS is global open source severity of unit score. The second part is about our model. My team member will make it clear in their part.
Hi, I'm Hanjiang. Relationships between variables and target through the implementation of visualization is essential. For people who have a faster reaction to process visual information than reading texts, it also helps us to understand the connections between our data and results. Through interaction with data, we're very likely to have discovery and discussion. The pie chart on the left upper panel tells us proportions of hospital death. The death rate, according to the original dataset, is 9%, which means that the feature is imbalanced in the view of the statistics. Nonetheless, in the perspective of medicine, 9% of the death rate under the Apache system is understandable and appropriate. Gender also could be a very important feature for prediction due to different physiological status between men and women. The line chart at the right upper panel describes that there are relative differences of average death rate between male and female, although both lines follow a similar pattern as age rises. The death rate of male patients is relatively higher than that of the female patients, such as at age 20, 30 to 40, and age 80 plus. The causation might be healthy, unhealthy habits of male patients, such as smoking, alcohol, and bad temper, etc. There's a tremendous amount of information that the doctors and nurses and all the care staff are encoding some of these notes that they take, and a lot of that is just harder to access. Nevertheless, data visualization brings the solution to us. By plotting heat map that shows the correlation of missingness between every 2 columns in the Apache covariate, we could easily recognize the correlation of missingness by seeing the depth of colors and numbers on the plot. In the missing number of matrix at the lower right panel, we can see that these features in medicine missing value are very informative. For example, a patient which is not doing a test may often mean that the attending staff did not think they needed it. Deducing probable values from other variables based on the domain knowledge, for example, surgery or ventilation status. Flowcharts indicated us the process of a project to obtain more accurate performance of models. Original data needs to be pre-processed, such as dropping missing values that occupy a little bit part of our dataset, or input statistical values such as mean, median, or even zero for those features that are important for our prediction. Next, we did explanatory data analysis EDA to summarize their main characteristics, often with visual methods. It decides a statistical model can be used or not. Primarily, EDA is for checking what the data can tell us beyond the formal modeling. For example, we used the Apache covariate features to explain the missing value in this dataset, which provides in a medical way that whether a patient needs to be tested or not. We also did a visualization, which is already introduced to let people interact with the data in a more transparent, informative way. Feature engineering, the process of transforming raw data into features that provides a better understanding of the underlying problems to the predictive models. Feature engineering enters data inputs into things that the algorithm, which is the basis of models, can understand. We need to assess how the results of a statistical analysis will generalize to an independent dataset. We subsample groups as training sets to train the model, then test sets on the remaining part of the test set as the validation set. The point of the cross-validation is to test the model's ability to predict the new data that was not used in estimating it in order to tackle the problems such as the overfitting and underfitting, and then the models are trained for the use of prediction in the future. We're ready to train our model. We can use them to estimate the generalization or performance accuracy on future data. Finally, calculating the cross-validation score and obtain AUC after certain times of iterations. Performing cross-validation and calculating AUC should be simultaneously executed for different models and a parameter setting in order to obtain more accurate outcomes. That's how we work on our project.
Here I'm going to talk about how we generate our model and the result we got. What do we want most is that we want both better performance and interpretability on our model. As you can see here, after we spend a lot of time on data pre-processing and feature engineering, we feed our data on both single and ensemble models, but we couldn't generate a high score of AUC. That made us really depressed. So we keep doing a lot of research about intensive care knowledge, try to find efficient ways to deal with the feature selection, and we keep searching for some new algorithm, such as XGBoost, LightGBoost, and the latest one, CatBoost. CatBoost uses a more effective strategy. It relies on the ordering principle and called target-based with prior, and it also has pre-built metrics to measure the accuracy of the model. Besides, it's very fast and easy to use GPU training. It also supports missing values and category features, which is really good for us. So we feed our dataset in this algorithm and got a good result. After we tuned the parameters and performed cross-validation, we got the accuracy score as 0.932 with 0.903 AUC score. Next, we want to interpret this model and try to get an overview of which features are most important for the result. So we plot sharp values of every feature for every sample. The plot sorts feature by the sum of sharp value magnitudes over all samples, and use sharp values to show the distribution of the impact each feature has on the model output. The color represents the feature value, which red means high, blue means low. In our model, this reflects that a high Apache for a hospital death probability got a higher hospital death, which really makes sense. Also, we can get the feature that contribute to each sample. It helps us understand the specificity of each patient so that the characteristics can help the doctors make decisions quickly.
Generally speaking, we've learned a lot from this project. First of all, analysts need to have background knowledge about their data, because some variables may have internal connections like causal relationship, which has a huge influence on dealing with missing value or selecting important features. Also, as a process to select a subset of relevant feature from modeling, feature engineering creates a new set of features that still capture most useful information, so that performance of models will increase because related and useful feature would be selected. What's more, using feature engineering is a good way to save computational cost and time, especially when dealing with large size of data sets, because usually we do not need every feature in data set to create an algorithm. Although we did a great job about this project, there are still some improvements we could further do. Firstly, try to use deep learning to improve prediction, because it doesn't require structured data when dealing with classification problem. Also, working on feature engineering to create a golden feature, which is most useful for modeling. Lastly, using adversarial validation to deal with potential overfitting problems, because comparing with cross-validation method, it could not only get some measures of overfitting, but also highlight which variables are responsible.